film number 3 on AD and DA converters will cover DA converters. And if we look at this measurement system block diagram, you see that DA converters actually comes later in the process than AD converters. But the reason why I cover DA converters first is that they are simpler than the AD converters. And also, actually inside some of the AD converters, you will find a DA converter as a part of the AD converter process. So therefore, we need to know a few things about DA converters before we cover AD converters. First, the converter basics. You have the analog signal here. You run that through an AD converter in order to get a digital signal, which is basically a set of numbers which says something about the amplitude at different time steps. So when we convert that back to an analog signal, we take the numbers and convert them to a voltage. So you get this kind of stepwise analog signal. If you run that through a filter, that will smoothen out the steps, so you get back your nice analog signal like this. Filters, some filters will remove sharp edges. Sharp edges, they are fast changes, and fast changes, they are best removed with a low pass filter. High frequencies are removed in a low pass filter. One possible way to create a DA converter is by using actually what is a summing amplifier. So this is basically a summing amplifier, but note that the resistances here, they are logarithmic in a way. The first value here, for example, could be 1 kilo ohm, 2 kilo ohms, 4 kilo ohms, 8, 16, and I guess if we had another one, it would be 32 kilo ohms. So they are so-called binary weighted. The idea here is to send a binary number into it, and the binary number here would either be 5 volts or 0 volts if we have so-called TTL levels, where the 5 volt represent a logical high and that one represent the logical low, or a 1, 0, true, false, on, off. So you send in either 5 volts or 0 volts. And then you sum the ones that have 5 volts, because the ones that have 0 volts will not contribute to the signal that is sent down here. Because you have 0 volts here, then you have a copy here, 0 volts. So if I, for example, have 0 volts here, there will be no current through that one, while 5 volts here will give a current through that one. So therefore the V out is based on the summing amplifier with a feedback resistor and the binary weighted resistors in the denominator of the equations. And the general equation for a summing amplifier, that was a part of the lecture series on amplifiers. So what I get now is a V out that is a function of 2 fixed resistor sizes and the level of the high. So in my case here, the high was 5 volts, and then you get this. So the V out is a function of binary combination, the binary numbers here. So that is a very simple form of conversion, and it, as you see, it doesn't use a clock, so it converts. Once you get a digital combination here, you will get an analog voltage out of the amplifier. But the disadvantage is if you have many bits, then the difference between the smallest and largest resistor will be very large. So for example, if you have 10 bits, then the difference will be 2 to the power of 10. So that is 1024. So basically, if you have 1 kilo ohm here, then you would need 1 mega ohm here. If you have larger, if you have, for example, 16 bits, then 2 to the power of 16 is 64,000. So the difference between the smallest and largest is really very large, and that makes it very difficult to get an accurate conversion, because the different resistor values are so they are very difficult to specify accurately. So in real DA converters, you will see this circuit, which is a so-called R2R ladder. Here I have numbers, but so they are just examples. The thing is that the ones that are vertical, like these three, they have double the size of the ones that are horizontal, like those two, with one exception, and that is the very first one, which has the same value as the vertical ones. So it's called an R2R ladder. Ladder in Norwegian stige, and with a great deal of fantasy, it looks a bit like a ladder, I guess. And R2R because those are the only two values that you will find there. I will not go through in detail how I solve this, but basically I use the basic rules of circuit analysis and get 4 equations, which I, in this case, chose to solve using MATLAB. And that in this case, with 3 resistors, 3 binary values, I get this as an equation. And you see, you get the binary value, voltage value divided by 8, divided by 4, divided by 2. So this means that if I have a binary value, for example 101, and this is my so-called LSB, my least significant bit, and this is my most significant bit, then a change here will have will make a great impact, while a change here will make a smaller impact on the output voltage.